So is everything a-okay in the technology? Okay. All right, so this is a QR code for the exam. We're gonna go over the spring 2017. If you just want to. Okay, so real quick before we get into nomenclature, I made you guys a little chart, and this is the priorities, and then I also kind of summarized the endings and stuff for the nomenclature that you'll need to know for this exam. Sorry. Okay. So definitely make sure you know your priorities going into the exam. There are a lot of new things on here, and a lot of them look pretty similar, so it's going to be helpful to know your priority. So at the top we have carboxylic acid, so that's going to be the highest. Next is going to be anhydride, although this one is less likely to be on the nomenclature. You're more likely to see the other functional groups. You've got your esters, you've got your acyl chlorides, amides, nitriles, and then some of the other stuff that we've gone over before, aldehydes, ketones, so some earlier stuff. So yeah, take a picture of this, look it over, and we'll go ahead and get into our nomenclature. Okay, all right, so going into this first question, we see we have this acyl chloride. So compared to all of the other stuff on the ring, this is going to be our highest priority. And so the ending for an acyl chloride, specifically a cyclic acyl chloride, the parent is going to be carbonyl chloride. And then the cyclohexane will come before that. So cyclohexane, carbonyl chloride. So this exam, you might have to spend just a little bit more time practicing nomenclature just because there are a lot of subtle differences. So for example, like the cyclic compounds versus the linear chains, some of these have slight differences. Like with this one, you have to put the carbonyl chloride after the cyclohexane. But anyways, then going around and numbering for our substituents, we're always going to start at the carbon that is connected to the parent chain. So in that case, the parent is acyl chloride, so acyl chloride is going to be number 1. And then we go around the ring towards this ketone. And so remember for ketones, the substituent name for those is going to be oxo, OXO. And this is on carbon 3, so we have 3-oxo. So we don't have any more substituents, so that's going to be it. The only other thing is going to be, we've got wedges and dashes, so we've got our R and S. So this is our chiral center. Hydrogen is obviously going to be 4, and then we look at the next carbons attached to it. So we have the carbon with the acyl chloride. So that one's going to be our highest priority because it's connected to an oxygen and a chlorine. Comparing the other two carbons here and here, they're both CH2s, so we're going to have to move on to the next carbon. So if we move here and here, we see that this one down here has got a oxygen attached to it. So this side is going to be our next highest priority. So this will be 2, this will be 3. So we've got 1, 2, 3. And then if we go around the circle, we've got R. And so our lowest priority group is on the dash, so we don't need to change it. We can just keep it as R. And that's going to be everything we need for this first one. So we've got R, and then we've got our substituent, 3-oxo. And then we've got cyclohexane, carbonyl chloride. Okay. Also, if you guys need me to speak up or turn the mic up at any point, just let me know. Okay, so that's going to be the name of our first one. All right, moving on to the second nomenclature question. So here we've got a carbonyl directly connected to a nitrogen, so this is going to be an amide. And so amides and amines for that case are a little bit weird. Any substituents you have coming off of the nitrogen, they're not going to have numbers, but you'll just denote them as N dash whatever the substituent is. So real quick, let's get that out of the way. We've got subs. And so our first nitrogen substituent is just an ethyl group. So that's just going to be N-ethyl. And then over here, throwback to the last test, we've got a benzene, and then it has a CH2 group as well. So this one's going to be benzyl. So we've got N-benzyl. So those are going to be our subs for the nitrogen. And then going back to just the parent nomenclature, so the ending for amide is just throwing amide at the end. Very original. And then it's just going to be the longest carbon chain of the alkyl side. So either way we go around, we get a 6 carbon chain. We go up here, it would also be 6 carbons. So we're going to have hexane amide, and that is going to be our parent. Hexane amide. All right, and then coming off this chain, we do have a substituent. This is just going to be another ethyl group. So this is coming off of carbon 4, so we'll also have 4-ethyl for our subs. We already did the nitrogen substituents. We don't have any stereochemistry that we need to worry about, so we're good to go on this one. And then just remember to do your alphabetical priority. So we've got benzyl, and then ethyl. So benzyl's going to go first, and benzyl. And then we have N-ethyl, 4-ethyl, and then hexane amide. So another thing that you could do with this one, specifically because we have 2 ethyl groups, you could also just write this as N,4-diethyl, but either of these would be accepted. So we've got N-benzyl, N,4-diethyl, or N-ethyl, 4-ethyl, and then hexane amide. If you were to get an amine, have you guys gotten to chapter 19 yet? Or yeah, okay. So I don't know if you'd see it on this exam, but it's the same thing for the substituents, the N. Anyways, go on to our last nomenclature question. So this one is definitely a good one to know your priority for. Nitriles we haven't really done a lot with nitriles. So you might see the alcohol and just get confused on your priority. But just remember, nitriles do come before alcohols. So the parent on this molecule is going to be the nitrile right here. And so when the nitrile is the parent, you actually do start numbering onto the nitrile carbon. Sometimes we've seen it where, you have whatever chain and the nitrile is the substituent. So when it's a substituent, you don't number onto the carbon of the nitrile, but when it's the parent, you do. So just be very careful about that one. That one's a tricky one. But so we have carbon of the nitrile is going to be our first carbon. Then we're just going to go and get the longest chain that we can. So we've got 2. We're going to go to the left because it's got the longer chain. 4, 5, 6. This one's also very unique. You just throw nitrile at the end. So since we have 6 carbon chain, that's going to be hex. And then we do have a double bond starting at 5. So we've got hex 5-ene, and then you just throw nitrile at the end. And then again, for these, you could also just do 5-hexene nitrile. So you could throw it in the middle, or you could throw it at the beginning. So that's going to be our parent. Now we just got to look at our subs. So we've got a alcohol substituent on carbon 2. Alcohol subs are hydroxy. And then also coming off of carbon 2, we have a 1, 2, 3. We have a propyl group. And this one's not any fancy propyl, it's just a linear chain coming straight off, so it's just regular propyl. And then we just have our R and S that we have to worry about. So we don't have to worry about E and Z for this one because the double bond on the left, the groups are the same, so we don't need to worry about E and Z for that. But we do have wedges and dashes, so we're going to have to look at R and S for carbon 2 right here. So we go to the next atom over. So we have our oxygen right here, so this is going to be number 1. And then the other groups are all carbons, but with our nitrile, that one's triple bonded to nitrogen compared to these two, which are just CH2s. So this one will get, the nitrile will get our number 2. And then the other 2 carbon groups, they're both CH2s here, so we'll have to move on to the next one. So we've got another CH2, another CH2. We have a CH3 over here, and then we have a C double bonded to a another carbon on the left. So we're going to go with the left side as our 3rd priority. And then over here on the right, that's going to be 4. So we've got 1, 2, 3. So if you go around, we'll get S for this one. The lowest priority is on a dash, so we don't need to change anything. So this one's just going to be S. All right, so we've got everything we need. We're just going to throw it together. So we've got S, alphabetical priority, so 2-hydroxy, 2-propyl, and then 5-hexene nitrile. Okay. Do we have any questions about the nomenclature? Yeah. Yeah, so the priority is just based on the functional group. And so nitrile does get a higher functional group priority than an alcohol. So if you see a nitrile and an alcohol on the same chain, the nitrile will win for the parent name. But then for RNS, that one goes to, that one's just purely based on the molecular weight of the atom. So the higher the molecular weight, the higher the priority. And so when we look at the atom that's directly attached to the chiral center, we have the 2 CH2s up at the top. We have a C here and we have an O here. So we're still looking at the C right here. So that's why the alcohol wins for the RNS. Yeah, if we had to move on to the next one, for example, like let's say they were all carbons, then nitrogen, then maybe that one would win. But yeah. Any other? Yeah. Yeah. So carbon is number 4. And then we have nitrogen and then oxygen, so that's why oxygen wins. And then that's why like bromine and stuff wins most of the time, because those ones are very far down. What's up? Atomic number. Yeah. The molecular weight increases too when you go down the periodic table. But yeah, that's probably a better way of putting it. The atomic number. Basically further on the periodic table. Yeah. That's just kind of a like a grammatical thing. Like if you did like hex and nitrile, it just kind of looks weird. So yeah, and it's kind of like with like hexadiene. So instead of hexadiene, it's it's just like a little thing. I think you wouldn't get points off for that, I wouldn't think, but you know. Okay. All right, we'll go ahead and move on to the facts question. But if you have any other questions about nomenclature, just come up at the end and we'll get that sorted. There's definitely a lot of stuff for this nomenclature, so. All right. Okay. Our first facts question, we've got a reactivity question. So we've got these benzenes with these esters on them, and we're asked to look at CH3O- Na+. So this is going to be strong base. You have your oxygen with its lone pairs. And so what this is going to do is this is going to attack the partially positive carbonyl carbons. So like right here, and right here. And so when we're looking at reactivity of these compounds, we see that the group on the right, the ester, is the same, but the only difference is going to be what's on the benzene ring. So we've got nothing. We've got a amine, and then we've got a CH3 group. So this sort of goes back to the aromaticity and stuff from the last chapter in the last test. So what we want for these molecules is we want a as partially positive of a carbonyl carbon as we can get. So we want electron withdrawing substituents to take the electron density out of that carbon and make it more partially positive. So for the benzene ring, we want electron withdrawing groups, and we don't want electron donating groups. Electron withdrawing groups will take those electrons out and make it more partially positive. Donating groups will kind of negate that and make it less partially positive by donating electrons towards the carbonyl carbon. So always remember, even if they're not drawn, nitrogen does have a lone pair. And so this nitrogen is actually going to be able to donate to the benzene ring by resonance. On the left we have nothing, so that one I'd probably look at last. Just compare the other two first. But we've got donating by resonance for the amine, and then over here we just have a CH3 group. But just remember, alkyl groups are donators. They just donate by induction. And so resonance is going to be stronger than induction, but they do donate. So we have nothing over here, and then we have two donating groups. So automatically this group on the left is going to be the most reactive because it doesn't have anything donating to negate the partial positivity of the carbonyl. And then comparing the other two, donating by resonance is going to be stronger, so it's going to be worse in this case. We don't want donating groups, and so resonance donation is going to be basically the worst case scenario. So this amine substituent will make it the least reactive. And then over here, this one's just going to be in the middle. Questions on that one? Right. Increasing acidity. Okay. All right, so for acidity, we want to look at the stability of the carbanion or the anion in general that forms. So stability of our anion. And so we'll just have to identify which which atom will form a anion. So over here on the left, we just have these two ketones. And so if you've been paying attention to your NaOET reactions, anytime we have a carbon in the middle of two ketones like this, the carbon in the middle is going to be the most acidic. So we're going to have this one be our carbanion. In this one, we have some carboxylic acids. And so we do have this carbon in the middle, but we also have a hydrogen that's just directly attached to an oxygen. So that one is actually going to be our hydrogen that we take off and form the O-. And that's just because the H oxygen bond is a more acidic bond than a carbon-hydrogen bond. On the left, we didn't have a choice because there wasn't any other acidic hydrogens, but here we took off the oxygen hydrogen. Then over here on the right, we have, again, this carbon here, and then we do have an ester carbon, but this one in the middle is still going to be our most acidic, just because it's got the two ketones in between that it will resonate with. So spoiler, increasing acidity, stability of anion. We want more stability for a more acidic anion. And so when we look at the negative charge, we have to look and see if it resonates with anything nearby. So in the structure on the left, this negative charge can resonate with the ketones, and it could resonate either way. So we've got two resonance structures here. With this structure, we have the oxygen negative charge This can resonate with the ketone as well. And so this would form a resonance structure like this. And then over here on the right, this one can also resonate either way. So we get two resonance structures here. Okay, so now we just have to compare them. And so when we look at these structures, we have the negative charge on a carbon. It's being shared between the carbon and the oxygens. In the middle, we're sharing the negative charge between two oxygens. And on the right, again, we're sharing between a carbon and an oxygen. So in the middle, since we're sharing between two oxygens, and oxygens are more electronegative atoms, this one is actually going to be our most stable and most acidic molecule, just because the negative charge is being shared between two electronegative atoms rather than one oxygen and a carbon, which is not as electronegative. So this one right here is going to be our most acidic. And we just have to compare the left and the right. So the left, there's not really much going on there other than the resonance structures that we already drew. Over here, though, we have this ester oxygen. And so what this is going to do is this is actually going to donate to the, it's going to donate towards the ketone. And so that's actually going to be decreasing the acidity of this carbon right here, kind of like what we looked at in the last question. It's donating its electron density towards the negative carbon, so that's going to destabilize it and make it less acidic. So this is going to be our least acidic. And then this one over here, it's just going to be in the middle. Any questions on that one? Mm-hmm. Yes. Mm-hmm. Yeah, so for acidity, it's always going to be based on stability. So you want to, when you're just looking at the anions, you want to delocalize that charge as much as possible. So you're going to want to have electron withdrawing groups that are taking the electron density away from it. Whereas if you had like a donating group like we do on the right structure, this would be putting more negative charges on a negative charge. So it's kind of preventing the charge from delocalizing. And so it's just kind of focusing it, and that makes it unstable. The most partially positive is going to be for carbonyls. So in the first question that we looked at, we were looking at the carbonyl carbon. Here we're just looking at a straight up negative charge. So sort of similar, but kind of different. But yes, you do want the charges being delocalized, taken away from that negative charge. Mm-hmm. Yeah, when you're donating electron density towards negative charge, it's going to destabilize it. So yeah. And then just be careful. You might have one that looks like an alpha hydrogen, but for this one, since we have the oxygen OH, just make sure you're looking at all of the molecule. When I first did this question, I thought I would destabilize or deprotonate the middle carbon, but that's actually not right in this case. I don't want to just say all alpha hydrogens. That's why I did the one on the left, because that one's actually right. So, okay. We'll go ahead and move on to the next question. All right, we've got acidity again. Okay, so all right, so we've got a carboxylic acid on each of these structures. So since we're looking at acidity, again, we're going to want to look at the anion stability. So similar to the last question, we're going to deprotonate these. And so the most acidic hydrogen on these is going to be the carboxylic acid hydrogen. So we're just going to turn all of these into negative charges. And then this one's kind of combining questions 1 and 2. So question 1, we were kind of looking at the groups on the benzene ring and how they affected it. And then in 2, we were looking at the acidity. And so we're kind of looking at both here. So we're looking at the anion stability of the O-. And then we're also looking at the group on the benzene ring to see kind of how it affects the negative charge. So again, we want electron withdrawing groups to delocalize the negative charge. So on the left, we just have an alkyl group. So this is going to be donating to the ring by induction. In the middle, we have a oxygen, or an ether, I guess, technically. And so since this one has got lone pairs, this one is going to donate towards the benzene ring. So this one's going to be donating by resonance. And then over here on the right, this one looks kind of similar to the second structure, but this oxygen is actually too far away to do resonance with the ring. So this one is not going to be resonating with the ring. And instead, it's actually going to be withdrawing. And that's just because it's not directly connected to the ring, it's too far away. So this one's actually going to be withdrawing by induction. All right. So like we said, we want electron withdrawing groups, and the only electron withdrawing group that we have is going to be this structure over here on the right. So this one is going to be our most acidic, most stable, most acidic. And then between these two, resonance is going to be stronger donation, and we don't want donation. So this is going to be the least stable and the least acidic. And then over here, this one's going to be in the middle. Questions on that one? Okay. All right. Got a free response short answer question. We love those. So we have a side product. We're asked to draw a structure of a side product in Claisen condensation. So Claisen condensation, this is going to be one of those reactions where we deprotonate an alpha hydrogen, and then we attack a carbonyl. Deprotonate. I spelled that wrong. Okay, so if you look at the structure on the left, we actually don't have any alpha hydrogens. This one's an oxygen, and this one has got 4 bonds. It doesn't have any hydrogens. So the only alpha hydrogen that we have is going to be in structure B. So we deprotonate this with our NaOET, We've got our deprotonated form here. And so for side product, we're going to draw something that we would not want to be our main product. So this is going to be a reaction usually between a molecule in itself or something like that where we don't get the intended outcome. So since we're given these two structures A and B, the intended outcome is to combine them. And so that would be by having the deprotonated carbon attack the structure on the left, structure A. But we're asked to draw a side product, so we're not going to draw this. Instead, what we can do is we can have the deprotonated version attack itself to form our product. So we've got our O- here, and we've got this, and so this is where we attached our new group. So that would be the molecule kind of attacking itself and forming a side product. And then this isn't really a stable structure right here. So I would go ahead and just draw the full Claisen product, which would be when the O- gets protonated. We're just going to be like this. So that would be a side product for this reaction. Questions on this one? Mm-hmm. So for Claisen, you can do it, and actually, I think it's called crossed Claisen when you have one structure that doesn't have an alpha hydrogen and then one that does. And so usually what that does is it kind of just ensures that you get the right product when you react compounds, because you're not having any other like side products form. Um, so this one, like if you got this in like a reactions question, this would be totally viable. But since we're asked to draw the side product, um, and the one on the left doesn't have an alpha hydrogen, the only side product we can make is when the structure on the right attacks itself. And so you're just kind of inferring that she wants you, or like theoretically you'd want to react A and B together because you're given A and B. So to draw a side product, the only other side product we could form is if the structure attacks itself. Mm-hmm. Down there, the aldehyde. Mm-hmm. So for alpha hydrogens, it has to be attached to a carbon. So the alpha nomenclature refers to, I'm not sure who came up with it. They were, I don't know. I don't know why they didn't just use numbers, but this is what the alpha like nomenclature kind of refers to. So you have the carbonyl carbon, and then the adjacent carbons are going to be alpha, and then the next adjacent are going to be beta, and so it's just a Greek letter nomenclature, so alpha, beta, gamma, and so this is why you see like beta, keto, whatever. But it has to be attached to a carbon. So since this one up here is an aldehyde, this is not technically an alpha hydrogen because it's directly connected to the carbonyl carbon and not an alpha carbon. So yes, that is a good question, but it would have to be attached to an alpha carbon. Does that make sense? Okay. I can help you afterwards. I want to keep going. I don't want to keep you guys too long. Okay. All right, so we're going to get started with our reactions. All right, so we have LDA for our first reaction. And so this is going to be a deprotonating agent. But this one is specifically a bulky deprotonating agent. And so what happens with this one is it will deprotonate an alpha carbon, but it's specifically going to deprotonate the less substituted or the less sterically hindered alpha carbon. So in that case, we're going to go with this one on the left because that one is less substituted. So again, we're just going to be deprotonating that carbon. So we are left with this structure. We've got our carbanion there. We have a benzyl bromide. So this one, so the carbanion is going to attack the carbon, and then the bromine is going to get kicked out, kind of like a SN2 reaction. Not quite, but we've got our benzene, CH2, and we've got okay. All right. So we just attach those two together. All right, and now we've got a primary amine. Okay, so whenever we have a primary amine, H plus, and a ketone, this is going to form an imine. And so for this one, it's going to form a double bond to the nitrogen, just where the oxygen is. So I like to just redraw the structure. CH2. So you're literally just replacing the carbonyl oxygen with the nitrogen. And then it's going to keep any R groups it has. You'll keep the alkyl groups, but you won't keep the hydrogens. And that's just because alkyl groups are harder to get rid of. So this is going to be our imine. So imine is the one with the double bond to nitrogen. You might also see an enamine question, and that's with secondary amines. And that one forms the enamine structure. But for this one, this is what we're going to form. So that's going to be our answer. Okay. All right, moving on to the next question. All right, so we've got NH3 and we've got it with an anhydride. So anhydrides are interesting. And so what this is going to do, nitrogen is a strong base, and so it's going to attack one of the partially positive carbonyl carbons, and then it kind of just kicks out the ester part of the anhydride, or the oxygen in the middle. So with this first reaction, this is going to open up the ring, so I'm just going to number my carbons. Got 1. Okay. And then the other side, the oxygen is going to form an ionic interaction with the NH4 in the reaction, or the NH3. Next up, we've got SOCl2 excess. And so what this does with a carboxylic acid, or the O- on the right, this is just going to turn this into an acyl chloride. However, on the left, we have a amide, and this reacts a little bit different with amides. So it actually turns the carbonyl amide into a nitrile. And this one is in your derivatives chapter, so chapter 21, if you want to go look at that one. So on the right, it did something pretty standard. It just turned the carboxylic acid O- into a chlorine acyl chloride. On the left was just a little bit different. It turned the amide into the nitrile. And I believe this is actually specific for primary amines. If it was a secondary amine, it would not form the nitrile. Okay, step 3, got our Gilman reagent. And so this one, it forms a ketone with one of the groups, one of the alkyl groups that's on that copper lithium reagent. So it's not going to affect the nitrile at all, so we'll just keep that the same. Then over here, it's just going to turn this into a ketone with that R group. So we had CH3. So this will be our final answer. Okay, moving on. Yes, so SOCl2, it will form an acyl chloride from carboxylic acid, or the O-. So that's pretty standard. With primary amides, specifically primary amides, it will form the nitrile. So yes. And I think Dr. Bean mentions that on the chapter 21, like the wheel reactions. So you can look at that for more. All right, going on to reaction number 3. Question number 3. Okay, so we have silver oxide, H2O. So this one is pretty unique. This one is similar to Tollen's reagent. It's not Tollen's reagent, but it performs a similar function. And so what this does is it actually turns a aldehyde into a carboxylic acid. And so this is a very mild oxidizing reaction. So it doesn't affect like alcohols or anything like that. In this case, we don't have an alcohol anyways, but it's a very mild reaction. So it's not like Jones or anything like that, but it still turns it into a carboxylic acid. And then we have COCl2. And so this one is similar to the POCl3 SOCl2 reaction. So this one just turns it into an acyl chloride. And then we have a secondary amine here. And so an acyl chloride with a secondary amine is going to form the amide. So this one's not an enamine forming reaction. This one's just going to form an amide. We're just going to attach that nitrogen there, and then it'll keep its two alkyl groups. We've got our two ethyl groups on there. And then step 4, we've got LiAlH4, then H2O. And so what this one is going to do is it's going to, this one's going to take the ketone and turn it all the way into the alkyl. So it's a little bit unique. It's not going to turn this into a alcohol. It's just going to go all the way to the alkyl. So we will get that will be our final answer. The acyl chloride?
Yeah.
Yes. So the enamine will just be when you have just a regular ketone. In this case, we have an acyl chloride, so it's going to react a little bit different. Yeah. Yeah. Basically, the nitrogen will attack the carbonyl carbon, and then the chlorine kind of gets kicked out. So, yeah. Yeah, so a similar question. The enamine is not formed because this one is an acyl chloride and not just a regular ketone. Yes. Yeah. So yeah, so this one, the chlorine is a good enough leaving group that the nitrogen can just attack and then the chlorine just leaves. So it doesn't really affect the ketone oxygen. Any questions on any of these three? That is a good question. So one hint is that we're only given just NH3, we're not given excess. So if it was excess, maybe. But this one's also actually on chapter 21, the diagram, or the reactions wheel. What? The anhydride reaction with the amine. Yeah. So if you'll notice, we have the NH2 over here when we had the NH3. So, I mean, I guess this kind of negates what I just said about the excess, but so when this one forms the NH2 with the first carbonyl, then the other NH3 will take the extra hydrogen and form the ammonium salt. We can look at it afterwards because I'm not coming up with the right words right now. But for the moment, I don't know if you have your notes pulled up, but for the moment, this is at chapter 21. But if you'll come up to me afterwards, we can look at it a little bit more in depth. Okay. Okay, we're going to go on to the next reactions question. Okay. We have a nitrile, and we have H3O plus and 200 degrees Celsius. Okay, so for this one, what this one is going to do This one is going to turn the nitrile into a carboxylic acid. All right, step 2, we have NaOH. This one is a strong base, so this one is just going to deprotonate our carboxylic acid hydrogen. And then step 3, we've got this acyl chloride. So this will just kind of add on. The O- will attack the carbonyl carbon, the Cl will get kicked out, and so this will just kind of add that group onto the structure. So here we formed an anhydride. Very cool. So that would be the product of those reactions. Mm-hmm. I want to say that that is for a different like set of reactions. In this case, since we just have regular NaOH, usually if it's something with high heat, it's a very specific reaction. But for this one, we're just given NaOH, so it's just going to act as a base and pull off the hydrogen. Okay, number 5. So this one's fun. This one's kind of like exam 2 when you had to do your the reaction similar to this one where you're given blank and you have to kind of synthesize it. So one thing to notice is that we have a ketone, we have an aldehyde, and then over on the product side, we have an amine. And then the ketone on the left is actually just totally gone. It's an alkyl group now. So one of the biggest things from this chapter that we've learned is going to be the acetal protecting groups. So you could see it written like this, or you might see it written like this. And so what this does is this reacts with a carbonyl carbon, and it protects that group from other reactions that we might do. And so aldehydes are also more reactive than ketones. So when we're given an aldehyde and a ketone, the acetal will selectively protect the aldehyde. So this is going to be our acetal and H+ for our reagents. And so what this is going to do is it's going to protect our aldehyde. We form that funny little cyclopentane kind of thing. And then our ketone is left alone again because aldehydes are more reactive than ketones. So step 2, here we're going to want to get rid of the ketone because on the right we don't have the ketone. And so what we can do for this one is we can do a Wolff-Kishner reaction. So this one is NH2, NH2, OH, and heat. And so what this does is it takes a ketone and it just turns it into a alkyl group. And again, that's the Wolff-Kishner. So a good one to know. And so again, what that does is it just turns the ketone into an alkyl group. So now we've got our group on the left is just an alkyl group. And so the next step we want to do is we want to get rid of the acetal protecting group. And so what you can do for that is you just throw H3O+ in the reaction. So just throwing H3O+ will turn the aldehyde back to normal. Okay, so we're almost there. We want to form an enamine. And so to form an enamine, we want to have a secondary amine. And so we just have these 2 methyl groups on there. So the amine that we're going to use is just going to be this amine right here. We've got CH32. and H. And then this one has H plus as well. And so that's going to form the enamine structure from the aldehyde. Okay, questions on that? Okay, we'll move on to question number 6. Oh, sorry. The problem with that is that the H3O plus will affect the acetyl group. So then with the LiAlH4 and the H3O plus in the reaction, the H3O plus will turn it back into the aldehyde, and then the LiAlH4 will reduce it. So that kind of, it'll get rid of the aldehyde as well. So the Wolff-Kishner is kind of one of those unique ones that we can use in this case where we kind of need to be careful about the reducing that we do. So that's a good question though. So here we have the Wolff-Kishner reaction, and then the next step is the H3O plus. For the LiAlH4 and the H3O plus, they're together, and it's kind of like you have to put them together. Just that's what the reagent does. So in that case, then you would be kind of screwed. There are some cases where it doesn't. I don't have them off the top of my head, but yeah, either way would be wrong. But so we're gonna go on to question 6. All right, so we've got our NaOET, ETOH. You're gonna see this a lot, and on the final, so you better start liking it now. But this one is going to deprotonate our alpha hydrogen. And so in this case, on the right, we have the oxygen, so we can't deprotonate that, but we do have this carbon here that we can deprotonate. Okay. I'm just going to write this as OET for simplicity's sake. So we've got our carb anion now, but we're not ready actually to go on to step 2. And the reason for that is with this carbanion, this very reactive carbanion, it's actually going to attack itself before we do anything with it. So this one is kind of a lengthy question, but we've got our first equivalent, and then this attacks. We've got O-T-H. Okay. All right. And so the next step for this one, we've got this negative oxygen. And so what this is going to do is this negative oxygen is actually going to come back and form the carbonyl double bond. And then this this ETO is going to be kicked out since an O alkyl group is a good leaving group. So this is like our condensation reaction. So all right, so now we're left with this structure. And I kind of wrote it poorly to see this, but you'll see that we have a CH in between two carbonyls. And so what's going to happen is this is also going to be deprotonated. So we've got our carbanion again. And so now we're ready to go on to the second step. So our second step, we've got a alkyl bromide. So this is just going to attach the alkyl bromide onto where the carbanion is. So we've got our, what is it? Okay. All right, we got this big old structure going on here. All right, and then our last step, we've got H3O plus and 180C. So this one is also one of our unique reactions. And so this is going to be our decarboxylation. And so whenever we have this with a ester group, so we have this ester group right here, this is basically just going to kick off the carbonyl and the ester part to form kind of like a carbon dioxide derivative. So that's why it's called decarboxylation. But basically, you're just going to redraw the structure just with that that group drawn. Okay, so this one was kind of a lengthy one, but this is what we're left with. So again, just for that last step, we just took the carbonyl and the ester part and just kicked it off. Okay, any questions on this page of reactions? Oh yeah, sorry. No problem. Like here? Yeah. So the first step was the deprotonation with the NaOET. So that's this right here. This is just an O ethyl group. Right here. Yeah. No, it's my handwriting is not great. Yeah. No problem. Oh yeah, sorry. Oh yeah, on the last one. Mhm. So yeah, so the reason for that is this NaOET is a very strong deprotonating group. So when you have it in the solution, anytime you form anything that's like any hydrogens that are very acidic. So in this case, this hydrogen right here is very acidic because it's in between two carbonyls. So once that forms, the NaOET is just going to deprotonate that as well. Well, that's kind of ahead of what you asked me. So yeah, so the first step we attack ourselves, and then we form yeah. So the O minus here comes back in and kicks out the OET group. And so then we're left with a CH here. Yeah. Oh yeah. Oh yeah, I got you. I got you. I'm trying to remember the specific name of it because I think it has a specific name, but there's so many names in this chapter that I can't remember it. um, yeah, so basically what James is saying is whenever you have this in the reaction mixture, um, the carbanion is a very reactive anion because carbon is not very electronegative, so it's not stable as an anion. So when we have this going on in our reaction mixture, once the carbanion forms, it's instantly going to attack itself on the carbonyl carbon because the carbonyl carbon is a partially positive carbon that the carbanion can attack, whereas it would take us some time to be putting that next reagent in. So basically, if you want to think about it like if you're doing it in real life, while we're trying to put the alkyl bromide in, it's already reacting with itself. Yeah. hmm Right here. hmm Oh yeah, so like right here. Yeah, so once it attacks itself, so here we attached to like another equivalent, so it attacked itself. So since we have this ETO group, that's a good leaving group. So instead of forming like an alcohol, like in an aldol reaction, the O- is actually just going to come back down and kick out the OET. So that's why we form this as just a ketone here. And so then once we have this ketone and this ketone, this carbon in between them, the hydrogen is going to be very acidic because it's between two carbonyls. So then with another equivalent of the NaOET, again, because we're kind of doing this in a reaction mixture, it's going to be reacting very quickly. It gets deprotonated, and then we go on to react with step 2. Yeah, yeah. This one is definitely very helpful to know. I haven't looked at too many of the other exams as of right now, um, but you'll definitely see something probably like this where it might attack itself. Okay. I'm going to go ahead and move on to the mechanism, just so I don't keep you guys too long here. Okay, so we've got this kind of weird dipentane structure, and then we have a linear structure in the end. So we've got a couple of oxygens here, and we've got H3O plus. Okay, well, luckily we're only left with one option, pretty much. We've got our H3O plus. One of these oxygens is going to take a hydrogen and get protonated. So yeah. All right. So since this is symmetrical, it doesn't matter which oxygen you decide to protonate. But we protonate this oxygen, and now it's positive. And so what will happen next is the other oxygen will kind of shift its electron density towards that positive charge. So it's going to attack there, and then it's going to kick out the protonated oxygen on the other side. So here, get attacked. Okay, so now that just kicks out the other oxygen to form an alcohol. And then, since this oxygen formed a new double bond and it's got 3 bonds, it's going to be positively charged. And so then what's going to happen is we need something to kind of relieve this positive charge on this oxygen. So we can take our H2O from our H3O plus reagent. And so this can attack the site with the O plus. So that's going to kick the O plus back out. All right. So now we got this going on. Still kind of funny looking. But what's going to happen now, we're going to have another equivalent of our H2O, and that will just deprotonate that water molecule that's attached. All right. So we're sort of getting there. Not quite. To go continuing in the forward direction, we can have the other ether oxygen and take another equivalent of hydrogen and protonate itself. And now what we can do is the alcohol attached to it can, sort of like in the first step, it can attack and kick out the positive oxygen. All right, so we kicked out that oxygen. Now we're in a linear structure and we're almost there. We just got to deprotonate that ketone oxygen. So another equivalent of H2O, just take that off. And then we were good to go. So this one was kind of back and forth with the oxygen and hydrogen, but yeah. Any questions on that mechanism? Yeah. Yeah, so honestly with this, sorry? What is it? Nitroglycerin? Okay. Yeah, so honestly with this one, I feel like this exam is a bad example of mechanism because this just seems too easy. Compared compared to the enamine and the acyl substitution and like this one is just kind of like hydrogens and oxygens, you know? Whereas you might see something a bit more complicated. So hopefully the exam that we go over tomorrow will be a little bit of a better example. But what I like to do is I like to definitely keep looking at the product while you're doing it. Sometimes you can get like kind of tunnel vision on what you're doing with the mechanism, but if you keep comparing what you're doing currently to the final products, it'll help guide you just to make sure you don't kind of go off track. If it's something that you struggle with, then maybe save it for last, just so you can have all that time that you need to work on it. I also like to try and keep track of any nucleophiles and electrophiles because that's all mechanism really is. Like for this one, in the first step, our nucleophile is going to be one of the oxygen lone pairs. And in this one, that's kind of all we have. Sometimes there's multiple. But then our electrophile will be this hydrogen from the H0 plus that we can take off. In the next step, we have a nucleophile here our lone pair, and we have an electrophile here. So that can help too, but yeah. But hopefully tomorrow's example will be a little bit better. All right, so let's look at our synthesis. Okay, so this one, you've got Aldol, you've got Claisen, you've got all those fun NaO, ET, ETOH reactions that are probably fair game, likely to be seen on the synthesis. As always, make sure you check in what you can start with: benzene, 3 carbon alcohols. And so the first thing I see here is that we've got a enone. So that's when we have an alkene, and then next to it we've got a ketone. And so this one is going to be specific to aldol followed by dehydration. So going backwards, the first step that we have is just going to be ETOH and heat. And so from that, we're going to get the product of the aldol reaction, which is going to be an alcohol. And then ketone over on the right. So going in the forward direction, this would do kind of like an elimination reaction. So this would take off the hydrogen, the heat would, actually I believe the oxygen would get protonated first, and then it would leave, and then the hydrogen would come in and form that double bond. Anyways, so going back from this, so I mentioned aldol. So this again is going to be one of your fun NaOET reactions. And the only time that you'll need heat is when you're doing the dehydration like we do here. So that's why we used heat up here, but not in this step here. But for aldol, we need a carbanion, and we need it to attack a carbonyl. So one thing for synthesis to keep in mind is if you form a product or reactant, I guess, that has multiple alpha hydrogens, just be careful because this is kind of one of those like, oh, synthesis, you need to have it produce the most yield possible kind of things. And so with this one, we can kind of see that. So if we form our carbonyl on the left like this, and our alpha hydrogen on the right like this, here we can see we've got a alpha carbon with hydrogen that we can deprotonate. There's not another alpha carbon here with a hydrogen. This one again is an aldehyde. It's not an alpha carbon hydrogen itself. Again, no hydrogen over here. So this one, these two reactants specifically are going to guarantee that we get this product here. If you form something that might give you like a side product, you'll still probably get credit for it, but it might just be it might not be the full credit. And then you'll get a little note that's like, oh, watch out for yield, or I don't know, whatever. But that's something to be careful with these alpha hydrogen reactions. But anyways, okay, so we've got our benzaldehyde. And so with this one, we've got our good friend co-huckyl alkyl cocoa. If you thought it was going away, it's not. And so that's just going to take us to our benzene. So we're good over there. Over here on the right, we have this carbonyl carbon, and then we've got the alkyl group on the left and the benzene. This one is also going to be an exam 2 reaction. This one's going to be our Friedel-Crafts acylation. So we're just going to have our acyl chloride, and that attacks the benzene and gets added on. So we're good there. We're not done yet though. We do have to actually work this acyl chloride back because it is technically an organic product. And so with this one, we're going to use some of our chapter 20 reactions. So we can use SOCl2 to take it back to the carboxylic acid. And then from here, pretty straightforward. We can just use Jones or your chromic acid reagents. We can go back to a primary alcohol. So yeah, very fun. Any questions on this mech? Oh, sorry, synth. Yeah. The Aldol? Mm-hmm. Yeah. So I broke it right here. And I did that so it would give me reagents that would work best for the synthesis where you form, no side products. But what this reaction will do, not necessarily, it could break into a ketone and a ketone. You just need you need something with an alpha hydrogen that can be deprotonated. So like your carbanion. So in this case, we would have our carbanion here, and then our carbonyl on the other side. And so then this will attack the carbonyl, that will get kicked up, and then eventually gets protonated to form the aldol product. But yeah, you need to form something that has your deprotonated carbon and then carbonyl. Yes. Yeah. I'm trying to remember the name of it. Oh yeah. I think it's like beta hydroxy. What is it? Is it beta hydroxy ketone? The aldol product? Or is it just aldol? Yeah. But it's just called aldol, right? It's not beta hydroxy ketone. Okay. What? Right here? Yeah, that's just our Friedel-Crafts acylation from last exam. Yep. It doesn't go away. Yeah. Oh yeah, you're right. I did forget that. That's probably why it wasn't recognizable. My bad. Yeah, that's the catalyst that we use for Friedel-Crafts acylation. I did forget that. Okay. Okay, let's go ahead and go on to our spec. Okay, fun times. Luckily, I would say the spec doesn't get very much harder for exam 3 and the final. The final you might see like an amide or something, but generally it's not, it doesn't get too much harder. Yeah. Okay, so we're just going to do our unsaturation formula. So we've got 26 minus 14 over 2, so that's going to give us 12 over 2, which is 6. So this one is kind of a higher unsat number. Sometimes we see 4, sometimes 5. 6 is a little bit crazy. But this definitely means we've got our benzene. So that's 4 of our unsats. And if we quickly go to the the proton NMR, we see in the 7 to like the 6.5 to 7.5 region, we have this 5 hydrogen peak. So this is the benzene region, and 5 hydrogen indicates that we have 5 hydrogens on the benzene. So that leaves us with a monosubstituted product, or monosubstituted benzene. Okay, so going back to the IR quickly, we do not have any OHs, unfortunately. We do have a peak over here at 1700, and we have something at 1630-ish. So these are probably going to be our ketone and double bonds. Keep in mind if you have a benzene that you will pretty much always see a carbon-carbon double bond just because benzene has carbon-carbon double bonds. But it looks like we also have a carbonyl-carbon. That's pretty much all we can get there. Luckily we just have a handful of peaks. So it's just starting from the right. Got CH3. We've got 1, 2, 3 peaks. So this is going to be next to do that wrong. So this is going to be next to a CH2 group. It's also pretty upfield. It's only at 1.5. So I think this one is just going to be regular alkyl groups. Going on to the next peak. This one's also CH3. But this one is a singlet. We only have 1 peak. So this one doesn't have any hydrogen neighbors. So I've got that there. We have a 2H peak pretty far downfield at 4 to 4.5. So this one is going to be a CH2. It's a quadruplet, 1, 2, 3, 4. So this one has 3 neighbors. So on one side, I'm going to say that this is going to be kind of corroborating with this group over here. But on the other side, there's not going to be anything because that would give it more peaks, but we only have 4. Okay, and so then the last peak that we have, this one's kind of strange. It's in 6 to 6.5. It's pretty far downfield, and it's only 1H. And it's a singlet, so it doesn't have any neighbors. So this one is pretty alone. So usually when I have the weird ones like that, I'm just going to leave them kind of till later. One more thing I want to look at is the carbon NMR. So just count the number of carbons that we have. We have 1, 2, 3, 4, 5, 6. It looks like 7, 8, 9, 10. So we've got 10 unique carbons. We do have a couple of bigger peaks here in the middle, and those are probably going to be relating to the benzene carbons. If you'll see there, the ones highlighted in blue, here, I'll highlight them differently actually. So in blue, these ones are going to be symmetrical, and in green, those ones are going to be symmetrical to each other. So that's why we don't see 12 unique carbons on the carbon NMR. It's just the benzene because it's a symmetrical benzene. Okay, so now we just got to put everything together. So we've got our benzene for sure. We have a CH2, CH3. It doesn't have anything next to it. We've got a CH3 with nothing next to it. What else do we have? We have a CH that's got nothing next to it. And that accounts for 1, 2, 3, 4, 10 of our carbons with the benzene. So we have 2 more that we need. And so I think we're definitely going to have our carbonyl carbon. Let's see. Yeah. Okay. Okay, so we also have, forgot to mention, we also have 2 oxygens. So one of those will go to our carbonyl carbon. And then most of the time when there's 2, it's going to be an ester or a carbonyl and then an ether somewhere. And I see that this 2H peak is very far downfield to the left. So I think this one is going to be connected to the oxygen. So we'll go ahead and update that. And I don't see any other peaks other than this one down here that's very far downfield. So I think this is more likely to be a ester than just a ketone and a ether somewhere. Because if it was a ether, then there would be another carbon that's super far downfield, but we only have the one that's a CH2. So yeah, 1, 2, 3, 4, 5, 6, 7, 8. All right, so we've got 9 of our 12 carbons. It's 12, right? Yeah, 12 carbons. So we need 3 more. We have the CH3 here. We have the CH. And I know that if I try to put this CH3 on the other side of this ketone here, that's not going to work because that's just going to cut off our molecule. So the CH3 has to be attached to something that's not this ketone, and it can't be attached to the benzene itself because, again, that would cut off like the rest of our molecule. So it has to be attached to a carbon something that doesn't have any neighbors. And so the only way for this to happen is if we have another double bond. Then this carbon doesn't have any neighbors, so it wouldn't split that CH3. Another thing that kind of points towards the double bond is this CH here. This CH also does not have any neighbors. So what this can be, I think the only option that we have is the carbonyl carbon. Because this carbon would not have any hydrogens. The other part of the double bond did not have any hydrogens. So this would allow that singlet splitting for that hydrogen. And so I think that's going to be our structure. So we've got the benzene, we've got this CH3 attached to this carbon in the double bond, we've got the CH for the other part of the double bond, and then we've got our ester. So if we count our carbons, we've got 6 in the benzene, 7, 8, 9, 10, 11, 12. Everything looks good. Okay, questions on spec. What's up? Oh yeah. Mm-hmm. All right. So if anybody didn't hear that, so James gave a couple of pointers. So he said that the 5 to 6 ppm for the, oh my gosh, for the proton at NMR is your double bond region, so your alkene. He mentioned looking at the unsats as well, and putting a question mark by that that unknown unsaturation number. So keeping that as a possibility for a double bond or like a carbonyl double bond or a carbon-carbon double bond. And then he also mentioned if you look at the carbon-13 NMR, and you will have the table, so it would be more helpful on the exam. But this peak down here at the 10th peak is one of our carboxylic acid derivative peaks. And so ester is a carboxylic acid derivative, so that is also another hint that you can use. For some reason, the blanks don't have the table, so I never use it when I look at the blanks. Yeah. I think it generally follows the proton NMR, where the more like oxidized stuff is further down left, but yeah. Okay, any other questions for this test? Any other sections as well is fine. Okay, well, you guys are free to go. Tomorrow, if you guys are going to be here, we'll go over the spring 22 exam. In the meantime, have a good night. Get home safe. Get some sleep.